All right, so we will have a first quiz at 11:20. So I will give you a 5 minutes break, and I will stop at 11:15. All right, so the first one is I would like to give a definition about consistent linear system. Okay, so a linear system is called consistent if it has at least one solution. All right, and we're called inconsistent if it has no solution. Suppose we have, excuse me, suppose we have an augmented matrix corresponding to a linear system. And after doing elementary operations, we end up with the following reduced echelon form. So for example, all right, suppose we have that. Okay, so now we look at the last row here. You see that there is, so if this is corresponding to a linear system, that's what, and equal to 1. Okay, so that's corresponding to such a linear system. And because of the last row, you can see that you can't have any solution, right? So that the original linear system is inconsistent. Okay. The other way is that suppose we have so this going to then you may select x2 equal to 0, x4 equal to 0. Then x1 is equal to 1, and the x3 is equal to -1. So So 1, 0 minus 1, 0, right? It's a solution. Go to B, right? And then this becomes, so this system becomes to be consistent. So this is consistent. And this is inconsistent. Sorry. So you may have questions about whether a linear system is consistent or not. Okay. All right, and so we will try to answer this question in general. So we write a linear system. Okay, with n unknowns. As follows. Okay, so right, so this is our linear system with unknowns. So that because we have it's unknown, so the matrix, the size of the matrix m times n, all right, and the unknown vector is n plus 1. The right-hand side vector would be m times 1. Now we can split the matrix A, the coefficient matrix A, column by column. So this is the first column of A, and then you have the second column A, etc. So A has n columns, okay? And the unknown vector has n components. N components. And you write down the right-hand side vector B. Matrix multiplication, because in this section we are talking about the matrix multiplications. We have to use the matrix multiplications freely, okay? And so with this expression, okay, now it comes to a row of columns. Okay, so row multiplied with a column vector. So you have corresponding, you can do the multiplication for corresponding components. So x1 multiplied with a1 plus x2 multiplied with a2, etc. And the xn, an, which is equal to b. Okay, so you have 3 different ways to express the same thing. Okay, here is, this is a standard matrix representation for a linear system. Okay, and such a linear system can be put into this identity, and the unknown becomes 2 coefficients of this sum. Okay, there are coefficients in each terms. Okay, and the coefficient matrix A are partitioned into columns. So you just put columns here. Okay. And this expression is called a linear combination of A1, A2, AN with coefficient x1, x2, up to xn. Okay. Right. So the terminology used for this expression is called a linear combination of the vectors A1, A2 up to AN, and the unknowns play as coefficients. So now the system Ax equal B is consistent. All right? It's consistent. By our definition, is that we have a solution. Means that we can find a particular specific value for unknowns, just like here. Okay? Just like here. So that it's consistent if and only if the right-hand side vector B is a linear combination of column vectors of A. So it shows that consistency of a linear system depends only on information provided by A and B. They are known, right? The only unknown okay. Okay. All right, so the question about the consistency of a linear system is to ask whether the right-hand side vector B is a linear combination of the column vectors of A. Okay. Do you have any questions up to here? Okay. So for our study, we give another definition. We introduce the concept of column space of a matrix A. Okay, so we say A is an M times a matrix. And we define column space of A. The notation is COL, column of A. And we write down its columns, all right? So now the column space is the set of all linear combinations of column vectors A1, A2, An of A, so i.e. With the set notation, so this is equal to alpha 1, A1 plus alpha 2, A2 plus alpha n, and such that alpha 1, alpha 2, up to alpha 1 are scalars. Okay. So you select all possible scalars to form all possible linear combinations and collect them together into a set. This set is called the column space of A. Okay, so now it is clear to put a theorem in the textbook. The linear system is consistent if and only if the right-hand side vector B is in the column space of A. Okay. Because if B is in the column space of A, then we can find alpha 1 up to alpha n such that this linear combination is equal to B. And then the coefficient alpha 1, alpha 2, alpha n would be a solution. Okay? Be a solution. Okay, and we have a more general definition related to the column space of A. In here, we form linear combinations by using columns from a matrix A, right? But indeed, when we form linear combination, the vectors may not can be taken arbitrarily, not necessarily from a particular matrix, right? So that we were saying that given, all right, k column vectors, say V1, V2 up to Vk. So suppose we can check k column vectors of dimension say M. Okay. Then the set of all linear combinations of Vi, I from 1 to k, is called the span. So I see the span of V1, V2 up to Vk. All right, and we have a notation for that. The SPAN of the set of the column vector. Okay, again, so you can see the column space of a matrix A is just the span of column vectors of A. Okay. All right. We recall in calculus the m-dimensional real Euclidean space N is M so Rm consists of m-dimensional column vectors. Okay. And then with this definition, we have an immediate theorem. So the system AX equal to B is consistent for all B in Rm. Okay, so A is given, of course, the coefficient matrix, and if we pick up B from Rm, okay, arbitrarily, and such a linear system is consistent. If this is true, right, then if only if the column space of A is just equal to the m-dimensional Euclidean space. Okay, so it gives you a necessary and sufficient condition. Okay. And we can have a simple proof. Okay, so this is actually from theorem 1.2.2, but I can see it. If AX equal B is consistent, i.e. has a solution equal to okay, then B is because of this expression. So B is actually alpha 1, A1 plus alpha 2, A2 plus da da da, plus alpha n, AN. Okay? So B is already a linear combination of columns of A, and so this is in column of A. All right, so since each B in Rn has a consistent so B in Rm implies B in columns of A. Okay. Because it says that if B is any column vectors in Rm space, and this says that Rm is a subset of column space A. But column space of A must be a subset of Rm. Why? Because there are linear combinations of column vectors, of m-dimensional column vectors, so that so this linear combination must be a column vectors of dimension m. Okay, so this must be true. All right, so this is said is a subset of that set. Conversely, this say the column space of A is a subset of Rm, so that they must be equal. Okay, so they must be equal. Okay, so this shows that this direction. How about that? All right, so since column space of A is equal to Rm, if B is in Rm, then B is in the column space of A, and which implies that Ax equal to B is consistent. Okay, by this theorem, if B, the right-hand side vector, is in the column space, then the linear system is consistent. Any questions? Okay, no. Now, we examined our questions in more detail. So now we consider a linear system where x equal to b having a reduced row echelon form. Okay, so okay, I'm sorry. Whose coefficient matrix A has a reduced row echelon form. Okay, so the matrix A has a reduced row echelon form U. Okay. All right, so this matrix already in reduced row echelon form. So you can see a future of this matrix. All right, so which shows that each row has a pivot. So you can see each row has a pivot. Okay, so that is the spatiality. All right, so now, and you can write the columns of U in the following way. Say here, this is U1, right? And you have U1, maybe U3, E2, EM, EN. Okay? Because this is M times N, the matrix A is M times N. It has M columns, M rows, and N columns. All right, so you have N columns here. First of all, U1, U2, U3 up to UN. But in here, the second column is E1, is the standard unit column vector. All right, we call E1. And this column is E2, corresponding to the second row. Okay, we have a pivot here. And the last one, this is EM. Okay, so you can see that in N column vectors, and we have standard unit vectors E1, E2 up to EM in RM. Okay, we have that. Okay, so we can see that. All right, and now we have. So we can consider linear combinations of column vectors of U, okay? Column vectors of U, right? As follows. 0 U1 plus alpha 1 U1 plus 0 U3 plus alpha 2 E2 plus 0 U5 plus plus alpha M EM plus 0 UN. Okay? So we have, so for alpha 1, they are arbitrary. On R, we form linear combinations of column vectors of U. So you can see that. We particularly put 0 for columns other than the standard univectors. Right? So the 0, 0, 0. And you can see they are alpha 1, alpha 2, up to alpha m. And because they are linear combinations, so you can see that this is in the column space of U. Right? And the alpha 1, alpha 2, alpha m can be arbitrary. So the implication is that is in column space of U. Okay? So the whole m-dimensional Euclidean space is just a subset of the column space of U. And of course, they must be equal. Because the column space of U is a subset of the m-dimensional Euclidean space. Okay? Right. So if we have a linear system such that the coefficient matrix has a reduced row echelon form U, okay, and we find that in this reduced row echelon form, each row has a pivot, and so that the E1, E2, EM, the standard univectors in Rm, will appear in the columns of this U. And when we do some linear combinations, some special linear combinations, only for those special columns, we find that every m-dimensional column vector will be in the column space of U. And so the Rm, the m-dimensional Euclidean space is equal to the column space of U. Any questions? It's crucial observation, okay? A crucial observation. And so we go back to here. Because of that, now linear systems with arbitrary right-hand vector will be consistent. Okay? Will be consistent. So that gives you a sufficient condition that you can do row operations on the coefficient matrix A. Okay? And at the end, you have a reduced row echelon form. And you look at every row to see if there is a pivot or not. If every row has a pivot, then such a linear system is consistent for every right-hand right-hand side vector B. Okay, so that is very good, a very positive result. Okay. Questions? Okay. Now we consider, so maybe I give you the conclusion so quick. So now it is clear is consistent for all C in Rm by theorem 1.2.3. Okay, so we know that if we consider the linear system Ux equal to C, then for an arbitrary C, then the linear system is consistent. Now, but I just told you that this original linear system also consistent for arbitrary B. Why? Because this fact just reveals that such a linear system is consistent for arbitrary C, right? From this theorem. So the connection is here. Since Ax equal to B and Ux equal to C with okay, so by row operations, the original linear system becomes to this linear system, right? And the U is in reduced row echelon form. Okay, so they are row equivalent to each other, right? The solution space is equal to the solution space of C. Okay, so then because they are row equivalent to each other, so as we just proved last week, that they will have the same solution set. Okay? And in here, we just know that the solution set contains at least one vector, right? It has at least one solution because it is consistent. So that the solution set for this linear system is also non-empty, right? And so this implies that Ax equal to B is consistent for all B in Rm. Okay. Okay, so we see the power of elementary law operations means that the procedure of Gauss-Jordan elimination give us a reduced row echelon form of A. Okay, and so that we can check whether each row of the reduced row echelon form has a pivot or not. If it is the case, All right. Then, by this discussion, we say that the original linear system is consistent for arbitrary right-hand vector B. Now, we consider the opposite situation. Okay, so now A has a reduced log echelon form. Okay, so you can see that in this reduced log echelon form, there is a row, at least one row, having no pivot. So it's a opposite situation to this one, because in there, the U matrix in U matrix, every row has a pivot, but in this U matrix, there exists a row without any pivot. So that means that there is a zero row, right? Zero row here. Okay. So the augmented matrix corresponding to the original linear system, okay, has a reduced row echelon form. Okay. Okay. Now, from here, so we consider this augmented matrix. So it is clear that Ux equal to C is consistent, meaningful, has at least one solution, if and only if the lambda i's, because they are corresponding to zeros in the coefficient matrix, so that we must have okay. So these lambdas must be all zero. Otherwise, the corresponding linear system is inconsistent. Okay, so in particular, so we look at in particular, we just let C equal to the standard unit vector in Rm. Okay, so we let C equal to okay. Okay, so that means that this is 0, 0, 1. Okay, so if the C corresponding to the last column of the augmented matrix is equal to E sub m, right? Just in particular, okay, a particular case here. Then Ux equal to the Em is inconsistent. Okay, so it's inconsistent, obviously, right? Inconsistent. So that the corresponding Ax Ax equal to B is inconsistent. Why? Because these two linear systems has the same solution set. So if the solution set for this linear system is an empty set, then the solution set of this linear system is also the empty set. Okay, so it's inconsistent. Okay. Thus, Ax equal to B may be is not consistent for all B in Rm. Okay, so we have two situations to see here. If we have a linear system and with a reduced row echelon form such that every row has a pivot, the conclusion is that okay, the conclusion is that Ax equal to B, the linear system is consistent for all B in the m-dimensional Euclidean space, right, for all. But if we have this situation with 0 rows, then this linear system is not consistent for all be in the m-dimensional Euclidean space. Okay? And so we can write down a theorem as a conclusion. So we conclude the discussion in above in the following two theorems. One point 2.4. So a linear system AX equal to B is consistent for all B in Rm if and only if each row of the coefficient matrix A has a pivot position. Okay? So that this is the sufficient and necessary condition that the coefficient matrix A has a pivot position. Okay, meaning that a reduced echelon form of A in such a every row has a pivot. Okay, so that corresponding to every row of the coefficient matrix A has a pivot position. Okay. Okay, this is the first theorem. Now, a linear system. Okay, so this is the positive part, right? AX equal to B is inconsistent. Okay, so a linear system is inconsistent if and only if its augmented matrix has a pivot position in the last column. Why? Here, it is inconsistent if and only if at least the one of lambda 1 up to lambda k is non-zero. Okay, so if you have a non-zero here, then by row operation again, then you can eliminate all the entries. Okay, and so there is only one here, and that one would be a pivot. Right, so this is the last column here, just like a 0, 0, 0, 0, 1 here. Okay, and this one is a pivot. Okay, this one is a pivot. So because this is one is pivot, so you can do the row exchange, right? To move And so the first 0 row in the coefficient matrix will have a pivot position. Okay, you can do the row exchange. Right? You can do a row exchange so that the 0, 0, 0, 0, 1, this row will go to here, this position. Okay. Okay. Right. So that the last column has a pivot position, means that the last column has a pivot, right, in the position corresponding to the first 0 rows of the U matrix. Any questions? Maybe I take the example. Okay, so suppose after a sequence of elementary row operations, the augmented matrix of the original linear system becomes to this augmented matrix here. Now we can do replacement to cancel these two non-zero entries, right? How to do that? For example, you multiply the last row by -2, add to the second row. You cancel 2, right? And then you add the last row to the first row. You cancel -1. Okay, so this comes to 0, 1. Okay, so sorry, by 2 replacement. Okay, so by 2 replacement row operations. Now, but this augmented matrix is not in reduced row echelon form. Not, right? Not. Why? Because that all the 0 rows in a matrix which is in reduced row echelon must be in the bottom of the matrix. So you have to do the row exchange. So exchange the 3rd and the 4th row. Okay, so now the augmented matrix now is in reduced row echelon form, because each pivot will cancel all the entries up and down of it, okay? Up, upper and the lower than it. You can see that. And so you can see the last column has a pivot here. It's a pivot. So whenever you have a form like this one, and such that at least one of the lambdas is non-zero, then you end up with a pivot in the last column just by elementary row operations. And so it tells you that the original augmented matrix has a pivot position, the 3, 6 position in this augmented matrix. Means that in the last row, in the last column. Okay. So this is the equilibrium condition. Okay. Okay. Any questions? Okay. So basically, we have solved the question about whether a linear system is consistent or not. And furthermore, we will have a sufficient necessary condition that a linear system is consistent for all possible right-hand side vector, if and only if each coefficient, each row of the coefficient matrix has a pivot position. Okay, so. Any questions? Okay, if no question, then I think we take a break, and we will have our first quiz at 11:20.